Hello and welcome back. In this video, we are going to explore periodic trends that exist that give us information about atomic properties. These are going to be very important to us as we continue and build learning of new topics and bonding and reactions and so on. And particularly for 1412, as you continue on to the second half, we will keep using these properties as well. Very important. All right. So within the periodic table, there are trends, different trends that we observe. And the first one that is most important, that dictates all the other trends, so we have to understand this particular trend and then use it to try to explain all the others. It is effective nuclear charge. Z, as you know, is nuclear charge, sub EFF, effective nuclear charge. And the definition for effective nuclear charge is the pull of the nucleus. Very important, we're focusing on the nucleus. The pull of the nucleus on the valence electrons, outermost electrons. Okay, let me give you some more information, then we're going to make a comparison and see what is the trend for effective nuclear charge as we go in different directions in the periodic table. What do we expect? Effective nuclear charge is not just the nuclear charge of the atom, but you also have to take into account the shielding from the inner or the core electrons. Keep in mind that we're focusing on the valence electrons, how the nucleus, the effect of the nucleus is felt out in the valence shell. Okay? So for sodium, what we're going to do now is to compare elements in the same group. Okay, so we're going to look at sodium and rubidium. Both of these are alkali metals. And sodium has 11 protons, has 2 electrons in the first shell, 8 electrons in the second shell, and its valence is in the third shell. So it has to go through these 2 shells and this many electrons to reach and have an effect on the valence electrons. Rubidium, which is in the 5th period, this is in the 3rd period, this is in the 5th period, we have a different number of shells shielding. But we also have an increased number of protons. So there are 37 protons in the nucleus. First shell, 2 electrons, then 8 electrons, then 18 electrons, then 8 electrons in the 4th shell, and 2 electrons finally in the 5th shell. Look how many shells that the nuclear charge has to get through before it interacts and starts pulling on the electrons in the valence. So there is more shielding as you go down a group. You get more and more layers, more and more shells, and with more shells, farther distance, more shielding, the lower the effect of the nucleus on that valence shell, even though there are more protons. Okay. All right, so as we go down, so this is the trend now. Effective nuclear charge increases as you go down a group. All right. And going down a group, again, you're getting more and more shells, and there's more shells that are shielding the valence electrons. Hence, there's going to be a decrease in the effective nuclear charge as you go down. Now, if we compare atoms in the same period, so let's pick the 3rd period. I have here represented sodium, which we've already looked at, and now we're looking at argon. Argon has 18 protons. Sodium had 11. And the shells, let me draw this again so it's a little bit closer and easier to read. So we're going to look at argon. There are 18 protons. First shell, 2 electrons. Second shell, 8 electrons. Third shell, 8 electrons. 18, right? Now, we have the same amount of shielding as we had in sodium because it's in the same period. And so the shielding effect is not the same. What is different is the number of protons. The more protons you have at the same shell, the stronger the effective nuclear charge. So you have more protons, more positive charge pulling on the valence electrons with the same amount of shielding. So as you go from left to right across the periodic table, you're going to have an increase in effective nuclear charge. Now, I did this backwards, didn't I? Increasing effective nuclear charge as we go up. Sorry about that. So the closer to the nucleus, the less shielding, the less layers in between the nucleus and the valence shell, the stronger the pull that's going to be felt from the nucleus on the valence shell. So effective nuclear charge increases as you go up, closer to the nucleus, less shielding, and to the right, there are more protons pulling at the same shell. All right, so the next trend that we're going to talk about is the size of the atom. Okay, so we have, let me put the first one up here, and I'm going to now put it in a distinct color because it's the most important. Effective nuclear charge increases as you go up and to the right. And remember, for each direction, we talked about a different rationale why it is what it is. So now for the atomic radius, an increasing radius size of the atom. This is going to increase as you go which way? Well, think about it. If you're going down a group, so let's say that we're going from fluorine, second shell is the valence, chlorine, third shell valence, bromine, fourth shell valence, fifth shell valence. The more shells that you get, the larger the atom becomes, right? So the further down you go, you have more shells, and the atom is going to get larger. Now, what about if you're not changing the shells? What about if you're going from sodium to magnesium to aluminum to silicon all the way to argon? What's going to happen? Well, you're not changing shells, but what is changing is the number of protons. And the more protons you have in an atom, the stronger it's pulling, and the stronger pull from the nucleus is going to cause the atom to become smaller. All right, so the atom is going to be largest with the less number of protons, so down and to the left. The atoms are larger in general. These are general trends, and you will find exceptions, specific places that have exceptions for a bit more in-depth reasons, and you can read about those in your textbook. The next trend that we're going to talk about is ionization energy, and I represent it as IE. I think your textbook calls it E sub I. It gets messy because when you start pulling away more than one electron, then it's going to say E sub I1, E sub I2, versus when I write it, I just say ionization energy 1, ionization energy 2, etc. So I will be using this notation. Okay, let's not worry about successive ionizations right now. Let's just look at what ionization energy is. And the definition for ionization energy is the energy needed to remove, ionize, that means going to N is equal to infinity. And we talked about this in a previous video. Exciting the electron to N equals infinity, an infinite level away from the nucleus. In other words, you're taking it out of the atom. To remove an electron, and symbolically what we can write it as, so we have some atom in the gaseous state. We put in a certain amount of energy. That's the ionization energy. And what happens is it loses an electron, kicks out an electron, and is left as a cation. Okay, so this is the equation that would represent what we're talking about for ionization energy. How much energy does it take to take away an electron from an atom? So we're going to have increasing ionization energy as you go which way? What's holding the electron that you have to overcome is the effective nuclear charge. the stronger the effective nuclear charge, the more tightly the electrons are held by the nucleus, the more energy you have to put in to take them away. So it follows effective nuclear charge increasing as you go up and to the right. All right. Now this is only for the first ionization energy. We will talk about successive ionizations in class. Okay, the next trend we need to talk about is this is electron affinity. Okay, so I call this EA. And electron affinity is the stability. Oh, now we're getting into a thermodynamic term. Stability of an atom in gaining an electron. Okay, let's go back and see what we have here. Ionization energy deals with removing an electron or losing an electron, how much energy that's going to require. Electron affinity is the opposite, is gaining an electron. Those are two different processes, so keep those straight in your mind. So if we write an equation here, we have an atom, gaseous state, gains an electron, and you end up with an anion in the gaseous state. And electron affinity is the measure of stability of the atom versus the anion, and it is expressed in joules. It is a thermodynamic value. The more negative the electron affinity, the higher it is, the stronger it is. Okay? The more likely this is going to happen. More stable the anion. Okay, so increasing electron affinity as you go which way? Well, let's think about what's happening. If an atom is gaining an electron, what would attract that electron? What would bring it in? What would hold it there? What would make it stay there? The effective nuclear charge. So the stronger the pull from the nucleus that's felt by that additional electron, the more stable it will be. And so electron affinity is going to be the same trend as we had for effective nuclear charge, except think about one particular case, and that is, what if you have, let's say we have neon or argon, one of the noble gases, right? Where would that electron come from? Argon, 1s2, 2s2, 2p6, 3s2, 3p6. And if this atom is going to gain an electron, where will the electron go? Well, remember, you feel electrons in order of energy, increasing energy. The next available energy is the fourth shell. Do you think adding an electron to the fourth shell with still 18 protons is going to be very stable? That's a whole nother shell out. That's not going to be very stable at all. And so this trend excludes the noble gases. So up and to the right, with the exception of the noble gases. So fluorine would have the highest electron affinity. Okay, the next one, we have two more to go, is metallic character. So increasing metallic character. What exactly is that? Well, we talked about properties of metals, right? Malleable, shiny, ductile, conducting, la la la. And in general, where are the metals on the periodic table? They are down and to the left. The nonmetals are up and to the right. Well, that's the direction for metallic character. The further away you get from this separation, the more metallic in nature that the atoms are going to be. Metallic character increases as you go down and to the left. Okay, the last trend, and this is going to take us now into bonding, is almost the exact same as what we talked about for effective nuclear charge. It is called electronegativity. And this is a really important one, especially for moving on beyond 1411 and going into the second semester of general chemistry. We are going to start comparing compounds and properties of compounds, not just atoms, based on the atom electronegativities that are in different bonds. Electronegativity, let me write the word, is the pull of the nucleus, so far, sounds the same, for electrons, almost the same, and here's the distinction, in a bond. Now, this is measured in bonded atoms. Okay, it's the exact same concept and definition, except one is just a free atom, and how the nucleus is affecting the valence shell, electrons. And for electronegativity, now you have two atoms bonding, and how the nucleus of each atom is pulling on the electrons that are bonded. Okay, the same concept goes, increasing electronegativity as you go up and to the right. However, since the noble gases don't typically bond, we're going to see these as the exception. And those really are the periodic trends that we need to be aware of. There's something that I want to point out to you, and that is we have two of these trends that have exceptions, the noble gases as exceptions, the electron affinity and electronegativity. Both of the trends that begin with the letter E are exceptions, so it's maybe something to help you remember those. And that, my dear students, wraps up our little tutorial on the periodic trends of the elements.